All right, so welcome back. This is the second installment of a mini lecture course on compact quantum surfaces. Elmar, the floor is yours.
So let me recall what we did last time. It's not very.
Just a second, because I have to say got it. Wait, don't touch anything.
Okay.
Because I have to click your permission on being recorded. Just a second, done, it's yours.
So make it. It's quite big.
If you go to draw, you have to choose a different.
Yeah, I looked very small last time. So I tried the bigger one. Okay, last lecture.
You mean previous lecture? Last lecture, right? Friday.
German. Previous. Thanks. Lecture. What we did was we quantized the disk. So A, D. So you remember that D was a unit disk. L2, D. So analytic L2 functions. Analytic functions takes a Bergman projection from L2 to Bergman space. And then for all continuous functions on closed disk. So the doublets operator EF acts on some analytic function psi by Bergman projection multiplication psi. So these are is a function L2, then we project to the analytic functions. So what do we know? We knew that the adjoint is given by taking the complex conjugate. We have seen on the generators that commutators are compact, which tell us that so now we generate an algebra, doublets algebra. So the C star algebra means that we generate. So we give a generating set. We can take any doublets operator, but it's enough to take the identity function, one, and we include all the compacts, which is not necessary, but we want to have always compacts as an ideal. So this is almost commutative. So if you divide the doublet algebra by the compacts, we get something commutative, and this then we get the star algebra extension.
So if you are writing that it's a C star algebra generated, you don't need T z bar, yes? Yeah.
Yeah, there's a reason why I order it. My aim today is to talk about the classification of conductors Fillmore. They classify normal operators, essentially normal operators. And then there's a difference of if you take S or you take S star. So we will reformulate our classification of essentially normal operators in terms of the star algebra extensions. And then happens that of course, S, the shift operator, is not unitary equivalent up to complex to S star, but it generates the same algebra. So you're right, I don't need it. So, but it doesn't hurt even here. I take also compacts, doesn't hurt. So we take here the doublets algebra, and we have seen the quotient. It's enough to look at the generator.
Let's forget.
It's CS1 And even, see, this is quotient map, but this quotient map has a very nice, this very nice form on these triplets operators. It can be seen as taking the function on the restriction on the circle. So that allowed us to define now our quantum surfaces. We have seen what's so we have seen the oriented closed quantum surfaces. So it's a lot of notation. So the idea is we take the disk, classical disk here, while inside is a fuzzy point, let's say, the compact operators. Then you assign arcs to it, A1, A2, and then we go back, A1 minus 1. So the orientation matters. Minus 1. As many as we need. Okay, so let's parameterize these arcs. Oh, looks sorted. A I minus 1. So we parameterize by CO1 to the boundary of the closed disk. So we take one for a oriented surface of genus G, we need 2 G arcs. The parameterization of boundary arcs such that, so if you take the quotient of the classical disk by identifying arcs, this should give homomorphic to oriented surface of genus G. Today I put it down, so it's not a product. And where AEI T is equivalent to AI minus 1T for all T for I's and for all T in the world. So it's only 1 point. And of course, any point
Like this inverse is kind of symbolic. We just need that this is different.
it's
Of the arc.
yeah, it's one of these arcs. So
Yeah, but it's not any inverse.
yeah, it's a arc with an inverse orientation. Orientation matters. And this just says it's an arc.
Okay, let's do a very simple exercise. Let's do a two torus. So just 4 arcs. How would you name it?
So that could be convex, I think.
Huh?
I call this one A1.
Okay,
I call this is arrow.
yes,
I call this one A2.
okay,
And then I reverse an arrow. And this one I call A minus 1. 1, and here I reverse the arrow and call it A2 minus 1.
Right, if you wouldn't reverse the arrows, you would get projected space. If you wouldn't reverse the arrows, you would get projected space. Right?
Yes,
Yeah.
yes.
But, have to look at its order. A1, that's, yeah, one projective space. And that's an,
RP2.
yeah,
Real project.
but now there's something. Cis, I always require the same point. Now, if you reverse the arrows,
Yeah.
then this could be another, this could be a B, this could be a Q.
Yes.
Then it's not a projective space because you have the projective space, but then one point you're identified. Well, if I say exactly this should be, because it's my condition. You will see, or today we will see, it doesn't matter. I can take any assignment, it's just the number of arcs that matters. It doesn't have to become, it doesn't have to be classically the same surface, but I get isomorphic systalgebras. So I get systalgebras that there's no.
Wait, but on the quantum level, no.
On the quantum level, on the quantum level. So I can say what means classically, a torus is the same as a sphere, and then you take 2 points and glue them together. Doesn't look like a torus, but is an isomorphic systalgebra.
So take a sphere, and then you pull out like 2 ends, and then you join.
Let's,
right?
yeah, let's try to construct a sphere with 4 arcs. So a sphere, I would take this arc, include with this arc. And then that's the same, yeah. This arc with this arc. Now I can call this is a starting point of this arc. I call this A1, and my notation this would be. I put A1 minus 1, A2 minus 1, A2 minus 1. So the number of arcs, the orientations are the same. Now this one I call P, and I force this one to be P. If you see A1, A2, it's 1 arc. If you don't pass by P, you call it Q, it's 1 arc and another arc that gives a sphere, but then we have 2 points identified. So you take the sphere and just 2 points you identify.
2 different points.
And this systalgebra, now, well,
It's like a torus in which you shrink one circle to a point.
then take this is this call this one P, call this one P, and then you identify.
Yeah.
And this gives the systalgebra that's isomorphic to the doors. This will be the result today.
But wait, is it true also classically?
No, what I mean, that's not even a surface.
Well, but I can still do the same for a classical to sphere.
Yeah, but then you clue some points, and at
Yes.
this point, it's not a topological manifold.
But I don't care. I care about the sister algebra. I take all continuous functions such a compound out of space, and I'm asking if it's. So in other words, I'm asking whether such a. This is basically what you're talking about. We have a 2 torus with one circle collapsed to a point.
No, I only collapse 1 point. That's why.
No, you collapse one circle and a 2 torus to a point.
Yeah.
And this is not homeomorphic to the usual torus, is it?
No, classical is not.
It's not. That was my point.
Okay.
So this is a quantum effect.
Yeah, that's a complete quantum.
So far, there's not yet quantified because.
I can be. Well, I can.
From the point of view of just sister algebra, it doesn't matter if it's not the manifold.
No.
Exactly. That's basically about.
Okay.
Exactly.
But now I can.
Which to make sense.
No. He said topological manifold.
Even if it is not
Topological
topological manifold, still it is a topological space, and then you can speak about sister algebra. That's my point.
Among topological spaces, topological manifolds for a class of topological spaces, which can be.
It is, but
They have special properties, but
after doing this operation, you would get something which is no longer topological manifold, but still it's a topological space. So
yeah,
it does make sense to ask about the corresponding sister algebra.
This is even a worse
Yes.
example because you can close these arcs and then they're done. Looks like a sphere.
Can I break in because I think there's kind of misunderstanding. So hi, Elmar. So
Something-
what you're writing down is you to take fundamental group.
What I don't understand, but
Can you hear me or not?
Yeah, we can hear you. Maybe I'll put you down.
Okay, so as I understand, you take your surface, you look at the fundamental group and do a standard construction of classifying space,
yeah,
right? It's just compact topological space. It
yeah,
happens to be homeomorphic to original manifold,
yeah,
right?
yeah,
That's all.
yeah,
It-
yeah. Nice example. What's that? For all these errors, you can include together and disappear. Then you have the sphere, but it's it's isomorphic to my quantum theories. So yeah, you can do a lot of strange things.
So the identification is just say up, the up points down, glued with the,
Yeah, you can clue. Okay, so
you draw some points to.
yeah.
Points just.
But again, what I need for the fundamental group is also the points are the same. But this one you can glue together, and this one you can glue together. And then just keep a point. It's a one compactification of this here. With which my algebra they become isomorphic to doors. So there's some strange things happening. But let me erase the strange things. I don't want to. Well, this is one of the reasons when I define my quantum surface, I do require that to call it a quantum surface, I require it has a classical counterpart. Then we talk about these algebras, that's where the strange things happen. Okay, so so let's look at the, to make it a bit notation a bit shorter. You can take all these equivalence classes happen on the circle. Now this is isomorphic to a wedge product of sums of circles. One. How many we have in the classical cases? And then C, my quantum surface, J, Q is stands for quantum, the triplet operators. That's a symbol map. And while these are the tell me there's a boundary condition. Let me see that's a function on that space. It satisfies the boundary conditions. Just a short notation. 1, 2, 3. And the subalgebra of the set. So again, I have to mention that I actually defined the whole family of such quantum surface because I didn't say anything about this order. Well, here's the condition I want to order them that we get a classical surface. We can choose non-order anything, you know, that by gluing and cutting, you can take lots of combinations.
So, okay, so now this is a subspace.
Yeah.
So S1, right? So this is a.
Yeah.
So this C of.
Yeah. This is actually S1 with identification of these points.
So it's a subspace of
No, the motion space of the sphere.
at a level of this one. No, first of all, as symbol T is in the function of S1.
This one is in function of S1, and then I wanted to have it in subalgebra.
Right. But this is a sub algebra.
Yeah, exactly. Subalgebras which do not separate these points. They satisfy boundary conditions.
Okay.
It's another word to say. Now, let's go. Now, I haven't defined the non-orientable. Non-orientable closed surfaces. One surface. And now I know already something happens with the isomorphism class. So I want to find one surface at the isomorphic. So in the oriented case, I already mentioned the order of these arcs don't matter much. You will see it later. But here it matters how many arcs are going twice and how many arcs are going with the inverse orientation. So I'll recall what the following. So if you have connected sums of real two-dimensional projective spaces, and you include whatever number of two-dimensional Dori. So here, let's say I take here K. And here I take N minus K. Half. Then this is homomorphic to P. So to keep this notation, it's N times connected sum of P of projective spaces.
How do you know n minus k is even?
Well, I start here and then I know this is even. Well, if I have this number, I have k, and then I add and add and add. Well, I know, yeah, I start with connected sum, then each torus gives me two circles.
I didn't get it. So you
I'm not saying,
start with k and then what?
well, I start to take connected sums.
Yes.
And I know if I take a projected space with a torus, I get 3 times the connected sum of a projected space. And I take it again. So this one gives always twice projected space. So
first
one torus,
You are fixing N, and then you are
no, not
shooting K of the same parities.
I didn't fix N, that was the questions. No, I just start. So I start, have a look. Yeah, now I know what you mean. How did I find the N? You're right. I find the N afterwards. So I take my torus, so I count to K, count here the Dori, let's call them M, and then I say, okay, I call this M, I take K plus 2M.
Sorry, I lost.
Okay,
Can you give some examples?
Okay. No, I know what you do.
M,
I find here M.
and then
Yeah, it's much better. So this is M.
N is equal to
Here I tell you what the N is.
N plus K.
Yeah, not much better.
So N plus 2M. Times.
No, K plus 2M.
Now it's K. No,
This is now comprehensible. Yeah, thank you.
okay. So since I noticed that I have to be careful, would like to make a definition. So it's classically, it doesn't make much sense, the definition, because it's all the same. These things, let me call, I did now.
So since this connected sum is associative, so you are saying that torus plus torus is a projective space.
No.
Projective space.
The projective space plus projective space is a torus.
No, If there appears one projective space, it's non-orientable. And then if you just the genius is one. Those gives you two properties of projective spaces.
Yes.
Now that's so
So this is equivalent to the fact that two projective spaces sum up
Yeah.
to a torus.
yeah. So the reason why I had this strange n, let me call this one n. It's again, it's impossible to read. So I'd like to make a definition, and this strange n came from trying to make this definition. So n k define such a connected sum. So n,
Or this
now
capital.
this n is k plus un. So I have a projective space. Classically, I have the n connected sum of projective spaces, but it's distinguished by doing first taking k times the connected sum of p and then n times the connected sum of t. And I have to distinguish because the classification result will say these constructions are in random case different. So, okay, now how many arcs I will need? My n says, so let A1.
So T here is S1, is a T, the torus.
No, it's the torus. It's the
Two-dimensional. T2, okay.
I stop putting powers.
Okay.
So P1, we start with arcs in the same orientation. A1, S, this is a K, P, K. And then I start with A, K plus 1 and inverses. So inverse means inverse orientation. And we stop. Now I can use my N, capital N. A N. A N. That's the from minus. Minus 1. So these are arcs, the parameterizations of the boundary. So starting and ending and on the same point. So such that so of course, what classically I will get is so it's a quotient. We know the equivalence relation is just the same by identifying R. This is, well, the connected sum of projective spaces, homomorphic. N times. But I have to distinguish that how I constructed it. Now, if I shrink this up to a point, I hope I can. It's enough if I tell you with words. Well, so it ends shrinking. So if we shrink the first arcs, which come with the same orientation, to a point, what does it mean? They all I identify all these points. So A, E, T, it's equivalent to P, J, S, whatever. Yeah, it's equivalent to all the others. A, J, S, D, thou, equivalent to some other A, what else are? Yeah, all these things, all these are identifying string to a point. We get exactly the M sum of connected sum of Tori. And shrinking.
So the first equivalence relation, you identify AIT with BIT. The first one.
Yeah,
Yeah.
here, yes, here I only take, yeah, well, this is the notation is different. So we take a J T is equivalent to B J T for the first chase. And then on the other ones, the same as we have. It's better. J T. So it's 1 point on one arc gets identified on 1 point of its corresponding arc. T. So J from K plus 1 until the end. Last arc, now we have K plus 2M arcs. No, N arcs. And P fixed. And here I say any point on arcs, shrink to 1 point. So it leaves me with these arcs with K plus 1 and these K connected sum of Tori and shrinking all these arcs that come with an inverse orientation in the same way.
So the point is that only these A's with -1 as a superscript, these are opposite orientation.
Yeah,
And B have the same orientation.
exactly, perfect. That's important. Okay, the orientation matters for my classification. And here, so the last one, N. N minus 1 to a point, it's the same way. Gives connected sum of Tori. Of projected spaces. So it's, the first that comes with the same orientation. Okay. So now it's clear. So C, okay, P. So I take an index with 2 parameters, K. So K has to be here 1, and I put a Q that's quantum. So doublets operators. So I apply symbol match, so I function on a circle. And maybe I now really use these arcs. So on the first arc, the AJ identified with the BJ. And then it takes arcs, what is arc, A, J, E, or M, maybe. Different. Here's the, okay, here's the, this operator is missing. So I take the functions on the circle. So I can try to take an I, A, T. It's the same as, so T, the functions will not separate these points. So here I take the A, I, inverse, orientation, B. So for all J runs from 1 to K. I runs from K plus 1 to N. And T is a fixed parameter in interval. So now we define all our closed quantum surfaces. We've defined families, actually. So what I want to show now is that all Dori with the same genus are isomorphic. And here they are isomorphic only if N and K agree. So, and
Sorry, so quantum connected sum doesn't make sense.
no,
So you are keeping from this connected sum only a motivation.
yeah,
What about is happening with these generators?
exactly. I wanted, there's two things I wanted to like to define systology first, which I call one surface. So I don't want to leave, so I want to have a classical analog. That's why I take these conditions that I take the classical quotient, I get something nice. Since I later noticed that the systology paths don't depend on if that it's a topological manifold or not, I really don't need it. But it's just, this is more motivation in this moment. Now I know that I have, it makes a difference. I have to count how many arcs come with the same orientation, how many arcs come with an inverse orientation. That makes a difference. That gives non-isomorphic systology paths. So actually, I just the most general version would be just here. I take that many arcs. One group comes with the same orientation, and another group comes with the inverse orientation. That would be enough, and then I can say, well, these are my quantum surfaces. We will see a very simple description of a generator with shift operators and unitary operator, if time allows me.
Can you give me a formula for genus depending on N and K? So imagine we are classical. I take capital N and K. So what would be the genus? Because it's non-orientable.
And
Sorry.
But even non-orientable genus, it's called Euler genus, and the Euler genus just counts
Capital N. Okay.
how many cross caps are in the connected sum.
And it makes sense also for non-orientable. Okay.
Yeah. Here I should say K. Well, it must be greater than 1, greater than 0. So if I take K0, then I get it all. So connected sum story.
Basically, so we are collecting a subalgebra of the Toeplitz algebra
All are subalgebras.
according to some boundary conditions
Exactly.
on the gluing.
Yeah, exactly.
That's a.
We have defined many subalgebras because
Yeah.
I can
Choose different. boundary-
actually I can even make one a big and another small. So there are many different subalgebras. So the subalgebras are many different.
Yeah.
So take one more. Okay. So the same as classifying which one are isomorphic. And this can be done very nicely with, well, it's a basic Douglas Fillmore theory. And this is nice that we have a problem in non-convex geometry, but it can be solved with very fundamental ideas and results from operator theory. And VDF theory started, so the first thing is,
Elmar, sorry, there's a question.
oh,
Line bottom.
Kleinbottle. Yeah, that's the what we need, you know. A1. Oh, I don't want to have. Who? And then I don't want to have, yeah, that's
A1.
ones. Who?
So no A inverses.
No inverses.
No, I don't need. This is I cannot have an inverse because that doesn't match my. So I have only two. If I have an inverse, I have a torus. But it's the crosscut. Two crosscuts gives a Kleinbottle.
But when you identify, what? You identify A1 with B1 and A2 with B2, right?
Yeah, maybe I.
So it looks like antipodal.
To change my indices. I know in the non-commutative case, doesn't matter. So no, they should be separated. Yeah,
Yeah, so
they should be separated to have something. What begins a razor? Okay. So A1, that's A1, and then I start with A1. Yeah.
What is N and K? I'm just reading the question. What is N and K?
N and K, so P and K
now K is equal to M because M is 0.
means that, so this means that it's I take, so, well, it actually, it's a notation which arts I take. So I take arts, I take arts that. So
Again. No.
and well. So this is a symbol. This is just to remember it. It doesn't make sense because this are homomorphic to a certain projective space. So to a connected sum projective space. So this tells me about K. Now it's N.
So the question is, what is N and K for the Kleinbottle?
That's the K2. It's a 2-2. Kleinbottle is K
Is equal to M.
2. Yes, twice in the same direction. So this K counts how many arcs come in the same direction.
Sorry, correct me if I'm right, but I always thought that the Kleinbottle on the one part of edges you reverse the orientation, but on the other part you keep it the same.
So what?
So this should be A1, B1, A2, A2 inverse.
Yeah, something like that.
What do you mean?
So if you glue,
Kleinbottle.
yes.
I better take.
So one pair is the same orientation, in the second pair is that. So this is like A1, B1 and A2 inverse.
Exactly, yes.
Yes, so I'm confused about this previous.
So this should be,
definition. The previous one is
so this should be
projective space.
So the Kleinbottle should be
Exactly, yes.
Yeah, that's true.
One's projective.
Yeah. Right. So one. So one comes in the.
M is equal to that. So M is equal to 1, K is equal to 1, N is equal to what?
The same.
N should be 3.
Yes.
That is
It by K and N was referred to K of 2M, so it should be like.
Capital N is K plus 2M.
Yeah,
So if K is equal to M and both are equal to 1, you obtain P3, 1.
Exactly, yes. Exactly.
well,
P1 instead of P.
B, N, what did N?
So K is equal to 1, M is equal to 1. So capital N is equal to
That
3.
was a good question with client portal, because now let me erase this. So what I want is clearly we talk about, so this gives, we take a parameterization. A1, B1, we go up to,
RP2.
yes, it's better to really to explain it on the arts. P, K, so this is K, and now I start
And what?
inversing.
Have N pairs.
Yeah, well, I need,
A,
so the N, I want to count the number of arcs. So I go
K plus one.
1,
AK plus 1
yeah,
minus 1.
yeah. And here, to explain the N should,
Capital.
at the N, I want to count the number of arcs. So I want to stop with the last arc N, and that comes with an inverse N minus 1.
Okay.
This is better. So I have,
Okay.
so after gluing pairs become a circle. N should tell me that I will get the quotient. So the quotient gives me the,
Okay, so I think that idea is correct, but something is wrong with this formula.
yeah.
Capital N is
What was wrong was my motivation with projective spaces and doors. I cannot write the client model as a connected sum of a projective space with the doors.
so.
That was my mistake.
So in other words, a capital N is not equal to K plus 2M.
Here I write clearly what I want to say. N should compute, is a number of arcs I'm using. K tells me how many arcs are glued in the same direction.
Okay.
Exactly.
The same orientation.
So in fact, we have 2 N arcs because
Yeah. Do an arcs, and after gluing, I get so that's what I wanted to have here. So after gluing, only on the boundary, what I get is wedge sum. The wedge sum of,
so now 2 1 is correct.
here it's N, and here J. So this N tells me how many circles I will get. And the K tells me how many times I go twice in the same direction. When they get something, non-orientable, K has to be at least 1.
Is there N equal to 2K plus M rather than 2M plus K? In the previous.
And the previous was motivation.
Difference.
I wanted to show that what classically, if as homeomorphic surfaces, I have to distinguish. That's was my problem. And so I gave some motivation with this connected sum, because we know what the doors is, we know what the projected spaces, but if we glue them together, they are non-orientable, so it doesn't make sense classically, it doesn't make sense to distinguish. But here I have to distinguish how these are, I have to.
Okay, and when you get these non-isomorphic sister algebras, are they perhaps a Morita equivalent or have the same K theory?
The K theory is different.
Okay.
No. The K theory, so the K theory is exactly the classical K theory.
Okay.
It's classic. So I can classify to say, okay, if I talk about an orientable surface of G not G, so I get the K theory, I can read it from the K theory. And the K theory tells me what kind of service I get. So in the classical examples, K theory classifies the service. So I have for any service, which that's why I would like to keep the classical counterpart. So K theory for my quantum service is the same as the K theory of the classical service, but K theory is, as you say, it's a rough topological invariant. It cannot distinguish between its number of arcs.
How about Morita?
Well, I didn't think about it. Sorry, that's a question I cannot answer now.
Actually, you can. Because the algebra, so you know that they are classified by K homology.
Yeah,
They're different K homology classes,
yeah,
right?
yeah. That's right. That's where I want to get.
So
That's
they are
okay.
isomorphic because
What?
they have different K homology classes.
Okay.
In K theory is not enough.
So K homology is
Homology.
more refined than K theory, right? You can distinguish better with K homology. Is it what you are saying?
Yes. It's a different invariant. It's a dual invariant, right? It's a different invariant.
Okay, so K homology classes are not equivalent, not the same, but K theory are the same.
Yeah. Well,
Okay.
we will see. Okay. Well, we can order
I don't know what is.
the case. No, we get the K homology is the dual of we have universal coefficient theory. We have notation.
Yeah.
We have finite generate abelian groups.
Yep.
K1 is what it
But how can we have no torsion? You have torsion in.
no, I think it's the K1 classifies. The K1 classifies me as the star G plus. Ah, right. Yeah, it's different. That's true. Yeah, yes, yeah, that will be, we will see that's different. Wow, he knows that from after 5 minutes.
You have good students.
There's a question in the chat.
Another one? No, these are already done.
What's the red mark on the?
Yeah, because I cannot use his cursor. I must use one.
Okay.
So basic PDF theory. Okay, I go to another.
Sorry, is it always so that if K homology groups are the same, then K theory groups are also the same?
No.
Or is it only the case in this example? I suppose that it's the very virtue of these examples, yes?
Since this example, it comes from universal coefficient theory. The K1 groups are freely generated. I have no torsion, and it's finite. And then I take the home function, and I get K homology.
Yes, but this is some specific feature of these systems.
It's a
But he said-
yes, because
It's
it's a feature of having a finite CW complex. Things are finite. So my generators that you will find generator is, well, what is the generator of K1? All these arcs generate an element in K1. But since I have finite arcs, K1 is finite. And they will survive, yes, there's no torsion in K1. So, yes, theory. And it started with very simple, basic questions, not simple, because the solutions are not so simple. So essential and normal operators. So A in pH such that normal means it commutes with its adjoint, and here it almost commutes with the adjoint. So it's compact. It's compact operator. Now, if we had this, if you look at the graded up our exact sequence to the bounded, to all bounded operators, then we get here the Calvin algebra.
Which is essential.
So this is the Kalkin algebra. Now, what does it mean? Entonces, A is essentially normal. If and only if it's normal, so its image in the Kalkin algebra is normal.
Generators.
So then we can have a look. It's a so this is the star algebra generated. By these operators, which is commutative. Is isomorphic to the continuous functions on the spectrum. Spectrum. So let's call it spectrum. It's an essential spectrum. So the spectrum that provides after checking into the Kalkin algebra. So I put the sigma here. Now, I can turn these to the study of essential normal operators in exact sequence for studying the exact sequence. So 0. Well, yeah, that is we have compacts. And I consider it exact sequence. Let's call it A. We take, well, maybe just to shorten notation, let's call it like XA is a compact set in X plane. CXA 0. Where the star algebra, which I obtain from the extensions, remember that I take C star algebra as the algebra generator. Well, we take fix A star 1, and since commutators are compact, we take all compacts. So this turns my problem of studying essential normal operators in studying the star algebra extension. And from here starts all the theory. Now we have the star algebra extension. We can say we can define equivalence relations. We can mod out trivial extensions, which are split, and then we get a group. And these groups are known because that's where Kasparov started. Well, these are KK groups. But before that, let's be
very not obvious that you get a group, yes.
Yeah, it's not obvious. And
Either the same group, but
it depends.
Very pure.
Yeah. So we have theorems and depends a lot of these algebras. Actually, it's a bit more simple because these algebra are nuclear and commutative, and you have only the compacts. Here it would be a bit more easy, but that was what Kasparov observed. So if I take here an algebra which is stable, and here a nice algebra with conditions, well, then I get a B functor. That's the starting point. So the first paper on Kasparov on KK theory started really from the classifications from the star algebra extension turning it in a group by Brown, Douglas, Fillmore. So, okay, now we want our aim is classify. So we want to classify aim. So our aim is.
Sorry, I have a question. I really never understood it perfectly. If you consider these essential normal operators, yes?
Yeah.
You can consider two such operators and say when they are essentially unitary equivalents.
Exactly.
And the definition is that there is a unitary operator such that the, say, A and B is A minus U, B, U star is compact, the difference, yes?
Yeah.
My problem is that this operator is assumed to be genuine unitary, not only essentially unitary.
Yeah, well,
What is the reason for stating this?
no, it's,
What,
the reason is that you can always use the unitary operator because if you classify system algebras, there is strongly what you are talking is when are these algebra extension strongly unitary equivalent. And what you say that actually I don't need a unitary on the Hilbert space, it's enough that it's unitary if I project down to Calvin algebra. This is called weakly unitary equivalent.
yes, and
But we have a nice situation where it's the same.
sorry?
We have a situation where strongly and weakly unitary equivalent are the same. Gives the same groups, gives the same equivalence relation.
Because the quotient is commutative. The C of X. If you had a non-commutative algebra there, then they would no longer be the same.
Probably, I was now thinking about the compacts.
In general, those two definitions are different. yes?
Yeah.
In this case, where the quotient is commutative, these two definitions are the same.
I
With the compacts that we have.
Yes, we always.
bring the compacts to have.
It's an extension of commutative by compacts.
Yeah, and the compacts, I would say the compacts allow me to get always unitary equivalent. I will use the isomorphism of the compacts are always given by unitary operator. So if I find something, well, I can define equivalence if I take here equal, or I can allow here morphisms. If I have an isomorphism between compacts, I can always find a unitary operator that implements it. And then I can lift it to the multiplier algebra, and then I have here the honest unitary operator.
Okay, so maybe the reason is that you would like to work to be more flexible and work with possibly different Hilbert spaces, and then the Calkin algebra does not make sense. You cannot speak about something which is essentially unitary if this operator acts between different Hilbert spaces.
That's
You speak to one Hilbert space,
Yeah.
you speak about essentially unitary.
actually have to talk always about the same Hilbert space because we need an addition, and the addition is okay. How do can I add some extensions? So the compacts on Hilbert space, I can take the Hilbert space 2 copies, and that's isomorphic to 1. So to define the sum of extension, I should define what's the Basti invariant. That it's a lift from here. It's a lift to my extension, and then I project down in the quotient. These are morphisms. Now I would like to add 2 morphisms in the same Hilbert space. What I can do is I take 2 copies of the same Hilbert space, but I identify it with the same Hilbert space. And then the compacts, the 2 times 2 matrix of compacts, isomorphic to the compacts. And then I can add 2 extensions with the same algebra.
Yes, but precisely for this reason, I would say that you would like to allow different Hilbert spaces. Yes, if you add to extension, you land in the direct sum of 2 Hilbert.
I know, but I need to get back. So I take direct sums of Hilbert space, and I always have to identify with the same.
Okay, but this is identification, it's not just equality. Okay.
Yeah, it's an equation, and it's kind of my choice how I do it. Yeah, you can do another identification, and then you have to demonstrate that the choice doesn't matter.
But all these choices are unitarily equivalent.
What?
all these choices are unitary.
Sure. So what I think, the aim is actually my aim, which allows me to find to give my isomorphism is, my aim is now to classify by essentially normal operators. By unitary equivalence up to compacts, right? Unitary. More
Essentially.
compacts. That's the idea. So let's see in let's see the simplest example which we know. Well, we have here. We started, all of my talk started with a doublets extension. And here you can already see how it works. S1, 0. So maybe I should tilt this doublets, eraser. And let's mix this, some E. This the ascending spectrum, so spectrum. We wanted the spectrum of sigma A is a term. And what are these abstractions? And then we say, okay, we have two. So having two that fits, so take another one. Let's say A prime, CS1, 0. And the question is, when is this, how holds this one? A star, and we work on the same Hilbert space. It doesn't matter, actually, A prime plus compact. Very compact. And U honest unitary.
In which algorithm? U is in
EA.
What is something wrong?
No,
U is unitary, like on the.
it's only in B of H for the same space.
Yeah, we keep
And A prime operators.
actually, yeah, PH, but I can allow here S1. So if you know, actually, I mentioned it now twice. If you know the Busby invariant, then this is really, you can take an abstract algebra, which is isomorphic. It doesn't have to be in the Kalkin algebra, but we can put here our quotient, and we take it as a subalgebra of the Kalkin algebra. It doesn't work. To think about it, an element which is, well, this is generated by a normal operator with spectrum S1. That's what we have. Now, the question is, when can this happen? And an obstructionist index. The index. So, well, so, well, it's a Fredholm index. Just to show you, the original question of compact Silver was, so we have an essentially normal operator. Can we find a normal operator and a compact operator? So it's an essential normal operator, always a compact perturbation of a normal operator. So let N be normal operator. So this essential spectrum Sn observable. So sie ist Algebra generated by n, so adjoint and compact, we are in the setting. Now, and we take, for example, the shift operator S. Uni.
Sorry, your sigma means what?
It's a. You can take this one, BH, in case you are.
Yes, so you should have written spec of sigma.
Yeah, did I make a mistake?
Yes.
With the extension spectrum?
No. Spec on
Yeah, I've got the whole word.
Very often people denote the spectrum itself by sigma.
Yeah, that's why I started right. Spec in the sigma is very often denoted as a symbol map and duplex extension.
I did note sigma by 6, so there's no problem.
Yeah, and it's a G by 9.
Yes. And degrees of freedom.
So it should be the because binary numbers. So as unilateral shift. So just to show you that there is an abstraction. Now the index, so with sigma and I want to have invertible, so it's a Federn operator. Well, here it doesn't see S1. Well, actually, it says essential spectrum S1. So 0 is not in the spectrum, it is invertible. So it's a Federn operator, and then we can check the index.
Wait, so n is normal or essential normal?
It's normal. I want to compare, so the question from BDA one.
Okay, gotcha.
So I have an essential normal operator.
No.
Is it unitary equivalent to a normal operator mod some compact? So, and I want, this is just a simple example to tell you, there's an abstraction and the index is an abstraction, and then we come fully to the theoremology.
So are you assuming that sigma of n is invertible?
Well, it is.
An assumption?
Yeah,
It is. Because spectrum is 1 and that's not 0.
Okay.
So we have an invertible operator. So it is a Federn operator, it has an index.
So it's not an assumption. It comes from the fact that.
Yeah, it comes from the spectrum.
Yeah.
but n need not to be invertible. Sigma.
No,
Yes.
exactly. So this normal operator, you look at this index. So we know that dimension doesn't have to be invertible of the kernel. So, and minus dimension of the co-kernel, but we can say, you know, that its range is closed, and then we take just the kernel of its adjoint. Now, since we can, the kernel is the kernel of this modulus, so I can write it its dim dimension of kernel and star n. And again, I can just the kernel of n star is the kernel of the modulus. Dim dimension of kernel of n star. But here you see that it's normal, it's n star n. So any normal Federn operator has index 0. And index of the shift, you know, it's -1. And then we see, so
Yes, but you also need the fact that the index is unsensitive to compact perturbation.
exactly, well, that's one of the ways to say that is, well, it's a continuous map, you have to show continuity, but then you say, yeah, if you would have n equal to s plus k, now you can put
Sorry, Elmar, can I ask you a completely
st
question?
or to s. Yeah,
Why is it the case that the dimension of kernel of n is the same as the dimension of kernel n star n? Can you tell me in one more?
so if
It's the same as the kernel of the
phi,
absolute value.
oh, wait, let's, okay,
Because the absolute value, okay.
yeah.
Okay, I got you.
Well,
Yeah,
it's.
yeah.
Just.
Composition.
Well, yeah, it's just taking n phi. So it's basically this relation phi n star and phi.
Yeah, you take the norm, yes, of course. Yeah. Mhm.
And yeah, so, naja, hand waving, you can say, okay, the index is continuous, which has to be proven, then I can this compact perturbation, I just take a homotopy, and then I can identify, so can say, okay, if the homotopic, actually, well, that's an important remark. So homotopy classes of platforms do not change the index. If you say that the index is just have, if you prove that it's continuous, so homotopy class is not. And here we see, well, they cannot be in the same homotopy class. Now, this is the index.
Even more is true. Homotopy classes of fretwork operators.
Yeah.
It is index Z. Identified.
Completely classified by index.
Yeah, exactly.
Mhm.
Well, I just would have to put in the doublets operators in my exact sequence. I just would have to put the bound operators and then look at the case theory, and then it tells you, well, you have the case theory of the compacts is Z, is the dimension of the projection. And then you just get it's isomorphic to the K1 of the Kalkin algebra. And that classifies your Fredholm operators. So interesting is again, so that is something trivial. Now we have index1, and you can so see, I was talking about making extensions in a group, no? And then we have index SK, it's K, and index minus K, and index S star N, it's N, and then you see what it means to get a group. All these operators have the spectrum to zero. If the index are different, they cannot be unitary equivalent. And the group you can see, that the group is isomorphic. So the group of extensions Z and is parameterized by the index, because we know that all the Fredholm operators are homotopic to some of this power of S. And here we have a representative for each of these classes. So that was an example. Now we go to our quantum surfaces. So, okay, we start with a oriented case. 9 or G. How I 9Q. Please, the Q is not a 9. So we write it like.
But it's Q bars, that's Q divided by 2 pi.
Yeah. Okay. Doublets operators. Such that, and this boundary condition, let me just write it like this wedge product. We remember that we had these curves and this is inverse orientation.
It should be something like belonging maybe to C or.
That's, to see style cheaper, I don't know. So, actually, we need to know the orientations, no? That let's really let's keep the curves, it's better. Because the orientation matters so much. So here we have A, B, D, sigma, T, and here we have a curve in the inverse orientation, that matters. T.
Could you just say that sigma of T belongs to torus of G without the Q?
What?
You say sigma of T belongs to continuous functions of torus mod G sub T
No,
without the Q.
No, what I mentioned is I can make arrangements with these arcs that don't give a torus. But still we have an isomorphic syzygy.
So sigma lives on the boundaries.
Exactly.
Yeah. Like, how is it called? Bouquet of circles?
Yeah.
Not like a torus.
No, I just meant that.
I know what you mean.
T sub G.
That the restriction would be a restriction of a function on the torus.
T with symbol G is something two-dimensional.
No. It's exactly the sum.
I know that what he means that it's, this is something like a restriction on the boundary. Now I say, if you restrict, then you get a function which is a restriction from classical torus.
Yes.
But I
the boundary.
But I don't want to say this because what we will see, the only thing that matters is how many arcs and what's the orientation. Now, I wanted to turn it. So actually, what we see is, of course, that we have P, the boundary, but here the functions do not separate the points. And by our equivalence relation, we get exactly this wedge product of circles. And it should be J S1.
Wedge sum.
Wedge sum, exactly. Now, this topological space I can embed as a compact set in the complex plane. So let's call it X2J. That's the number of circles which I define as, okay. So union of 1 plus 2J circles. I want to have some, so I take S. Here, what I put in parentheses is the center. And then I multiply to get a radius of 1 plus 1 J. So S that 0 is the circle, Z minus that 0 is equal to 1. And here I change the radius. So these circles, well, I've seen this drawing. I can draw circles. Let me try. 1. No, it's not a circle. So then it should look like the. Oops. So it's a finite. Oh, yeah. Well, that doesn't. So something like this. So finite. Aha. Finite Hawaiian urine.
2G copies, right? Exactly 2G.
Yeah.
But you're missing an A.
And that's important, that's finite, because otherwise.
An A.
What's missing?
Hawaiian.
Hawaiian, an A. Yeah, and it's important it's finite because otherwise K homology and K theory are not the same. One is the sum and the other is the product. So, okay, now. So I take this is compact in C, so I can view it as a spectrum of a essentially non-operator. And we can get a representation of one. So now let's say Z. We take Z as continuous functions on X to J, which separates the points. So it's identity function that do it. X plus I, Y is X plus I, Y. So it's identity function. Now we pull this element as this function, we pull back to the circle. So we have a quotient map. Let's say P goes from our boundary circle. Okay, let's keep that boundary to the quotient.
This should be pi.
This pi. Is that okay?
So this is not a torus.
Yeah, that's not a good idea. Let's call it rho or something. Otherwise, let's take it rho. And then we can from there we can go to, well, we can even make it like this. So we have here the rho that you know it's the canonical the quotient map, and then we have our phi. Maybe it counts the numbers of circles to our X to J. And then we set some trig zeta we define as the pullback. So we have first we apply this rho, then we apply phi to J, and pullback. It's identity function. Now, this is a function on C on the boundary of the circle. We can have a look at it. It's a central spectrum. So, we want to have it's on the boundary circle. We extend it. So, the extension of R, E, I, theta. You multiply this R, so you have continuous functions on the closeness. So we have our zeta on the boundary. So then we consider our Toeplitz operator. So the Toeplitz operator of this extended function. Now, if we look at this Toeplitz operator, we apply sigma, our Toeplitz operator. Our theta. Well, that's the restriction to the boundary is our zeta, and we see that the extension spectrum, so the spectrum of D is exactly our xn. X to G. So, and it satisfies because we have this composition with rho. It is an element. So it's an element in C P 9. Oh no, how to make it a G. Q. The algebra which separates. Now we know that it's our projection of the Calculus algebra separates the points. So we know that the system algebra generated by our sigma c, so d theta, what I did, this adjoint, I could leave it. This is exactly isomorphic to our c x to j, or it's isomorphic to our functions on the boundary circle. So we get all, that's it. So all functions, so we take d, d boundary circle motion. So all the functions which satisfy the boundary condition can be approximated. So the algebra generated by these doublets operator, and the compacts is isomorphic to our non-commutative one. So this one now is G Q is isomorphic. So we found the generator. It's the algebra. E theta A, what I take this. I joined at 1 and to compact.
Sorry, Elmar, can you remind me what is the zeta hat?
It's extension to the closed disk. So there's here.
Yeah. Ah, it's 2 dots. Okay, sorry.
It's
Yes. Oh, yeah.
It was purpose of my definition of duplex operators in its function on the closed.
I didn't notice these 2 dots.
Yeah. So to make it on a continuous function. So these are our now we have generator, and then we can ask. So this gives us the same. What it gives us systolic algebra extension with the same systolic algebras.
So could I just quickly look at where's the spectrum of T zeta hat?
Yeah.
The sigma of T zeta hat?
Well, that's the feedback. Yeah. It's, yeah. You're right. I just essential spectrum. You're right. Sorry. The duplex operator, and the spectrum is the image of the function on the circle, and that gives you this compact set in the complex numbers. Now we want to know. So we know that we find generators. Now I have to find generator. And the question is, if I take other generators, when are the unitary equivalent? But our interest is not to classify essential nomic operators. We wanted to find isomorphism classes between these quantum surfaces. So now assume that alpha is an isomorphism between our some G, and let me take some isogenius G prime, or 9s are not good, N, no? Whatever. It's an isomorphism. So we have the Jacobson and the current ideal is are the compacts. So we get
I'm confused. So this is T with what?
T with some N
And G and
some G.
G prime G, what?
Orientable of genus G and genus N. Assume that
Two different parameters.
Just your
Depends for what.
Q1, Q2, if you like.
So this one is not G, it's Q, okay, and this one,
Okay. Let's, yeah, I don't know, it's this, so this is 9
G.
Q. And here we can take, which is much more common, we take a G prime.
yeah, this is what I expected, this part. And C,
You did like my nines. So some other G prime,
like a 9, I just object to calling it G.
9.
Now we are asking whether the.
Now, okay, now.
Yes.
So the first thing is, we have the Jacobson here, the intersection of all ideals as compacts. So it gives us an isomorphism between compacts.
So are you asking now whether this genus classifies these quantum surfaces? Or in-
No. Yes, I want to say when are these quantum surfaces isomorphic? And instead of this, of finding an isomorphism, I will show that for a fixed G, we can give an active generator, and they are isomorphisms. Always a unitary equivalence up to compacts to an explicit generator, which is shifts and
No, we just compute the index of the generators.
yeah,
Right?
yeah. Well, the index tell me what will be the result? We have index 0. We need the circles, so we take a bilateral shift, and then the classification theory of contact as Filmer says all these quantum surfaces are direct sums of bilateral shifts and also compacts.
Yeah, but from the construction, you have this number G.
Yeah.
So now we are asking whether this G classifies these surfaces.
Yeah, actually, you're right. So that's its notation is not very clear. I even can take G equal G and say I don't care about. I even put and make different assignments of R's. Yeah,
Instead of G, you are taking what as this
I
environment?
take what I should. Anyway, we can discard different G's because we have different essential spectrum. And then the question is different assignments of R. So actually I can, so if I want to be, well, we know that G has to be G. So, okay, let's erase everything.
Okay, so classically as well, now the G classifies oriented flow.
I wanted to prove much more. I just wanted to, was lazy in notation.
Okay, so instead of
Okay.
you are considering what?
Okay. You remember that to find the quantum surface, we assign R's. So let's take two families of R's. So now, I don't really, like, on one code, it's the essential spectrum, if there's the number of arcs are different, the essential spectrum will be different. This one we can discard, there will be never there will be an isomorphism. So we look at the same, we take assignment of arcs.
The problem is that in order to define this algebra, you use some additional information, not only this G, but you didn't include this additional data in the notation.
Yeah, exactly.
Why
Exactly.
that's the problem? Yes.
I didn't, because in the end, I know they are isomorphic. Now, the data are the arcs. And now I give the data, so that A1.
More careful notation would be T with all this data, all these arcs.
Let's pack it as the boundary condition depends on all this combinatorial.
Okay.
Even if in a lattice file, I write all these arcs, it's half line. So, but now so we take two kinds of assignment, so, and it makes even the proof much better.
I guess maybe
Okay.
the upshot is that, we have constructed a operator like T of this, zeta hat, right?
I will construct it.
Yeah,
now.
just constructed now, we have it. Right?
Yeah, I didn't actually tell you because I didn't use the data. I didn't tell you.
Phi use the data.
Yeah, that phi,
Yeah.
this phi is also important because the phi has to identify the data. So I swept a lot of things under the carpet.
Okay.
And now that's the reason is actually the notation we can see the arcs. Now here we take these arcs. And let's take B, alpha B is better to see the difference. So if we don't have the same number, we don't have the same circles, we don't have isomorphism. Actually, I could say could take one and show you what is isomorphic. It's enough to say each one is isomorphic with such a kind of. I don't need to take two copies but yeah, the first argument will need it. So such that both yield something our circle out standard notation.
But G is common.
Excuse me?
G is common. Yes.
Yeah, G is fixed. Now I need that. The first thing which I need is that. And no, yeah, I should really. Now I need to. Okay, now I need giving. I need really to let's take a different giving. So I need a different definition. So how do I denote? So it's a.
You can use letter A and B. Somehow.
G
refers to these arcs, yes.
Put G equals 5, put G equals 6, then we can understand. Take some.
Okay. May I, please, Elmar?
Yeah.
So you have an extension by compact operators of
Yeah.
the functions on a bunch of circles.
Yeah.
And you're asking when the extension is isomorphic.
I want to give the generators. Actually,
No, wait a second. You're
Yeah.
asking when the extension is isomorphic.
Sure.
The C-star algebras when isomorphic.
Yeah.
Now, since compacts are minimal ideal, then
Yeah.
isomorphism of C-star algebras introduces isomorphism of the compacts,
Exactly.
isomorphism of the quotients.
Exactly.
So there's the same number of arcs.
Yeah, the thing which I would add is I want to give how they look like with generators with a bilateral shift. That is very, very concrete. So it's just let's put the one and giving just let's. So and this is the only I need. What Richard said. So if suppose they are isomorphic. Alpha GQ. So this is the other one. That Q an isomorphism. And exactly now it's a minimal ideal Chekhov ideal. This gives me an alpha from compacts. And all these isomorphisms are implemented by a unitary operator. Well, you take a one-dimensional projection, then you take the one-dimensional projection on the other side, and then you access all the compacts, you construct the Hilbert space. That's basically the idea of the proof. So there exists an U alpha in pH such that alpha of the compact is U alpha K. So it's a unitary isomorphism. Now, compacts these algebras are into multiplier algebra, so you can extend it uniquely to the multiplier algebra. And now any of these operators can be, the isomorphism is given by U T U alpha star. And then we are exactly in the situation when we have strongly equivalent extensions. And these are classified now by K theory. Now these,
But do you know that this is respecting the generators you have in the quotient, right?
yeah, that will now, we will need this phi. So we have this phi, takes the quotient the quotient to the circles. So that was a union. So circles with center and some radius. Okay. This can be used to order. So this phi can be used that we have a phi and we have, let's call it a phi bar. And this we can use the orientations. And here we have numbers, so we can arrange it that A1 and B1 go to the same circle.
This is under alpha, under U alpha.
Well, that doesn't matter. And well, I identify the circles and I find a generator, and I can always map these generators with unitaries in a generator of my algebra. That is the result for the classification. So there is an X cube. So the extension, we have this X, I called it X something, X2G. So our extension are always about these wedge product of circles. Well, compacts, which is, I can take C, but this is classified. Now we have U1 gives me a strong unitary equivalence. The algebras are nice, compacts and nuclear. So these are classified by K1.
You have pressed something very.
No, there was someone to share the screen.
Meeting verlassen, verstanden. You are viewing Konrad Schmidt's screen.
Verstanden.
So Konrad has taken over your lecture. This will stop screen sharing. Do you want to continue? Yes. So Konrad started sharing his screen.
Okay.
Wait. I still have to put. So it wasn't your fault, it was Konrad. Sorry, this is wrong. No. Oh, I should disallow screen sharing to other participants. You need this. Okay, now we are good to go.
It doesn't. So
by the way, since we had this interruption anyway, and Richard asked me this question by email, This is not the seminar, this is a lecture course. So if you have any questions, ask them now. I mean, there is no time for questions. Time for questions is always during the lecture. So we have like still 10 minutes, you know, ask any time you want.
So, why doesn't draw?
Doesn't know.
Should draw.
Circles?
Yeah. Before.
Okay.
Okay, this, you got, why don't you,
No, click draw.
Draw, click draw.
again, no,
Yeah.
Yeah, now it should work.
Oh, no.
Take another pen. Take another pen. I don't get it.
Try the thicker line, maybe that.
we're taking another, so let's take just that.
Try the thicker line, maybe that button will work under the draw.
Yes.
Oh, that's terrible.
Are you,
Maybe different color.
okay for you?
Yeah, but wait a second. I mean, this is ridiculous. This shouldn't be happening. I mean, I can draw.
Yeah.
It's crazy. I've never seen it before.
Yeah, use the thicker line.
Yeah, but like all of a sudden the touch screen is not working. Yeah, but I cannot write in such thick lines. This is crazy. I completely don't understand it. Try now.
No, no.
I have to sit down with the mouse.
Yeah, I think the mouse stole the capability.
Wait, I'll just stop sharing again. And start sharing again. There. And I'm gonna try to. Okay, please try again, maybe now.
But why is this toolbar is so gray?
Yeah,
Is something wrong with this? It should be black.
or red should
Be red.
this, yeah.
Yeah.
No,
For you, it won't work, but not for.
Look at this, what I get.
yeah, wait, something is
Leaving a trace, but
I-
it disappears.
I have a mouse.
Stop for a second, because when you touch it, I cannot use the mouse. I have some remote control. Share clipboard, no. Whiteboard.
Maybe I use this 6 lines just to finish.
Yeah, but I honestly, I mean, the remote control I have. Waiting for me to control the screen, but you are no, sorry, no, this was wrong. This was wrong. Leave mouse keyboard control, stop remote control now. So the problem was with here. Right now.
There's no bar.
Yeah, I have a bar here, but it's. Okay, try it right now.
Without
Yeah, so apparently it doesn't want to you to write with thin line.
Okay, I did.
Let's try again.
Well,
Are
I
you sure? Yes.
Okay, try again. No evidence is no longer accepting, that's totally bizarre.
that's what I hate on computers. There's no reason, no logical reason why this doesn't work. I can finish it.
Yeah, I'm afraid you have to, so you have this big line.
Okay. Well, anyway, I have not much time now. The extension which so this extension can be made in a group. And I keep this, well, these are my X to G. And let me keep here the compacts. But that is, in our case, with this nice the style sweeper, it's K, X, G. Well, C, it's K stabilization of C, and this is K homology. It's a K homology of, I take here the C style sweeper, X to G. Now this, the K homology is very well known. So, so K, 1, C, X to G is, that's where really what conductors film theory was celebrated, because it's completely algebraic. Algebraic topology, but here it's very easy. Well, I take the product, but we are finite. So let's number the connected components A in I. So the phonus is very general. So you can do it for any compact set in C. So these are bounded connected, bounded connected components and in the C complex its complement X to G. And as there's one component that goes to infinity, we don't take it. And each one has one set. And now the reason why I was starting with the index. So if you have an element here, so
Why are you using this notation? Like a coproduct is just it?
if you have, for example, the infinite Hawaiian earring, this is K homology. This is really the product. The K theory is a sum.
Product.
It's infinite.
It's wrong.
What?
Doing the product.
Yeah,
So it's like pi.
you take it.
Yeah.
Yes, of course, but this is a union or coproduct.
Well, these are, the incident numbers.
To write even the direct sum, it would be better.
Well, in our case, since it's finite,
Okay, but you are taking.
finite. Let me take something which is correct because it's finite. We can take some. Okay.
Yeah, but then
Infinite case, you take full product, yes?
yes,
Full product.
Pi is the
but this is pi, not V of us.
That's interesting because I took it from Blackadder, the symbol.
Maybe you had it upside down.
Yeah, probably. Yeah, actually.
Not the only mistake in Blackadder.
Excuse me?
It's probably not the only mistake in Blackadder.
is correct.
I don't know. Yeah, probably. But that's true. I learned it from Blackadder and I remembered it. This is simple. Okay, here it's finite in our case. And the map is interesting. So we have here in our generator an element.
You know, you have 30 seconds.
Element goes here, goes up to, so we have these sum, and then you take the index of our phaton operator T minus lambda J. So lambda J is in this component, Yj. So then it's an invertible operator. In the calculation algebra, it's a pattern operator, it has an index, and this is the way we can classify our essentially normal operators. Now, I have shown because of this isomorphism of the complex, if you have isomorphism of these style algebras, we get strongly equivalence classes of these style extension and this U, but which are introduced by the isomorphism of the complex, gives me unitary equivalence of generators. Now the question is, when are the unitary generators equivalent? So here it is, if it defines the same T class, now we know this index is the winding number. We are talking about, if we take our day T, which is theta hat, these are functions, also if I take the sigma, these are functions on a circle, and winding numbers are always zero. So each R comes with an inverse R. So that one goes to straight to zero, only zeros. All of them. Whatever generator I did, they are always good to zero. And it doesn't matter how I arrange R's. Yeah, I can take this phi, which makes the portion of the circle maps into the compact set C. I can use it to order my R's, which one is the first, and I can flip orientation in case it's necessary. And then get always an index zero. So there's a U alpha T, my generator, U star, which is up to compactor, let's put here mod ones. So up to compacts
Are alpha, yes.
mod, yeah, well, yeah, mod compacts is, I can take here the direct sum of p literal shift j equal to 1. So how many circles I have to j? And I want to get the spectrum, the essential spectrum. So I take my j plus 1 j u, and then I shift the sender -1 over j. So all my closed orientable quantum surfaces are unitary, are isomorphic. This is algebra generated by the compacts and cis operator.
They're not quantized.
Should it be U?
U is I have to say the Hilbert space. H is the sum j from 1 to 2j, L to Z, and this U is a bilateral shift. U A N is A N plus 1, A N plus 1.
So your extensions are all split, always split.
No, but yet it's compact. So
Trivial index, so that means.
yeah, these are trivials. Yeah. These are the trivials. So see, the oriented case are always trivial, but the non-oriented there's some effect which is not split. Yeah. So the oriented quantum surface are split. That's true. So I have not time for the others. The others we get winding number 2, so we take twice the shift operator. And then the numbers of shift operators, that makes the difference. So I think time is over.
Yeah, so you continue on Friday.
Yeah.
Stop recording.
I hope to have a bit.